This is AQA AS Physics 2020 Paper 2, Practical Skills and Multiple Choice. Unfortunately, I can't show the paper on screen, otherwise AQA will get the whole channel deleted like they nearly did in the past, but link to the paper and the mark scheme are down in the description. So first thing we're being asked is, why does the ray not change direction? Well, it's because we have this semicircular block, so therefore it always has to be exiting at 90 degrees to the surface, so it exits perpendicular to surface. Or we could say angle of incidence is 0, because of course the angle has to be to the normal, and we can see that the normal is in line with the ray there, or rather the other way around. Nice start so far, 1.2. So she draws an arrow, marks the path with ABC, removes the block, determine using figure 2 the refractive index of the block. Okay, so we can see that on the protractor, well, with the normal is of course here going in. So this is our angle of incidence, this is our angle of refraction. And we can see that going round from 0, that's equal to 66 degrees. And then coming out, it looks like if we were to draw a line there, looks like it's going to be something like, well, it's 180 degrees, isn't it? And then that's going to 200 and, is that 18 degrees? So it seems like that's going to be 38 degrees. Let's get Snell's law. N1 sine theta 1 equals N2 sine theta 2. I always say start off with Snell's law, even if there's another version of it available. I always like starting with it because it helps you avoid any mistakes, that kind of thing. So of course N1 is just going to be 1, so that just disappears because it's going into the block, so the refractive index of air is 1. We're looking for N2, therefore N2 is going to be equal to sine theta 1 over sine theta 2. And so that's sine of 66 degrees over the sine of 38 degrees. And you end up with, well, let's go to 3 sig figs, 1.48. 1.3, we have this travelling microscope setup. I swear I've seen this before. I know I've seen this in a question before, in a past paper. That's so weird. Okay, whatever. We're just being given this equation here. So all we have to do is pop in the numbers. Nice and easy. So just 20.02 take away 5.74 divided by take away 10.31 instead. And we end up with not quite 1.48, but 1.47. 1.4. We're told that the absolute uncertainty in all the readings is 0.04 mil. So therefore, absolute uncertainty in one value take away another, well, there's that uncertainty in that and that. So therefore, all we're going to say is that it's 0.04 plus 0.04, it's double. So it's going to be 0.08 millimeters. Even though we're taking away values, the uncertainty is only going to increase. Just remember that the only time that uncertainty decreases is when we're square rooting or cube rooting an answer, for example. So we're being asked to find the percentage uncertainty in n. And so we know that, well, we have R0, R2 minus R1. So in here we have 0.08 millimeter absolute uncertainty, and the same for the bottom as well. And so therefore, what we have to do, because we're dividing two numbers, we have to find the percentage uncertainty of the top and the bottom and then add them up. So therefore, we're going to say percentage uncertainty in R2 minus R0 is equal to, well, it's going to be that 0.08 divided by, what was the value? Well, it was 20.02 take away 5.74, wasn't it? And then of course we times by 100 if you want to turn it a percentage uncertainty. You can skip a step if you want to by not timing it by 100, because we're going to have to turn it back into a decimal eventually anyway, but whatever. And that gives us what, 0.56%. And then the percentage uncertainty in the bottom, again, is the absolute uncertainty divided by the value. What was it? 10.31. And it gives us 0.82%. So therefore, adding these up, we end up with 1.38%. And if you gave your answer to 2 sig figs, 1.4%, you'd also get the mark. So don't forget that whenever we multiply or divide two values, we need to add up the percentage uncertainties. 2.1, we have this circuit, all to do with EMF and internal resistance. Okay, so we're being asked, why do we include a fixed resistor in the circuit? Because our voltmeter there is measuring the terminal PD, and then we have our variable resistor at the bottom there. Well, it's because, let's call this one R1, let's call this one R2. If R2 is reduced to 0, current will be very large. So we could say battery could be damaged, so we could say battery damage or drained quickly. And actually, it means the EMF will change as well if that happens, because the EMF of batteries does change a little bit as it drains. Or you could just not decrease the variable resistor down to 0, but whatever. 2.2, we have this graph. We have our data points with error bars. We're being asked to find the, the minimum gradient. So don't forget that whenever we have a gradient, it must pass through all of the error bars. I'm surprised that it's going to pass through, but I guess just about. So we want the minimum, so it's going to be the shallowest line, so it's going to be going like that or something like that. Don't forget that it doesn't have to hit the bottom of this error bar, and it doesn't have to hit the top of that error bar. It just needs to be the minimum possible gradient that goes through all of the error bars. And you should, of course, use a big triangle to calculate your gradient, not a triangle like that. It should be at least half the size of the graph, and you should end up with a gradient of about 1. But there is a leeway of plus or minus 0.1 according to the mark scheme. 2.3, we're told that the maximum gradient is 1.3. So then we're going to use these two values to find out what the internal resistance of the cell is. Of course, we know that the gradient is equal to internal resistance. So therefore, whenever we have a minimum and a maximum gradient, we're going to take the mean. So mean gradient, yes, we could add them up, couldn't we? We could say 1 plus 1.3 divided by 2, but we can see there's going to be bang on in between the 2, so it's going to be 1.15. But we can't give a value really to 3 sig figs because our data is only 2 sig figs really, because if we look at the graph, the voltages are only going to 2 sig figs, 0.4, 0.41, etc. So therefore we should probably call that 1.2. But again, if you end up with a slightly different answer, that's fine, so long as your method is correct. 2.4, we are told that the line passes through 0.94 and 1 and 0.37. So we have a current of 0.94 amps, and we have a V of 0.37 volts. We're looking for E, so therefore we have to crack out our equation. Epsilon is equal to IR plus IR. Of course, this here is just the terminal PD, so therefore we can just say that's equal to V plus IR. So that's going to be equal to 0.37 plus that 0.94 times our internal resistance, and it gives us 1.5 volts. But I guess we should probably go to 3 sig figs, seeing that 2 decimal places anyway, because that's what our voltage is given to our PD. So I'm going to call that 1.50. Question 3, okay, so this looks like forces in equilibrium. So we have there 35 degrees and we have there 12 degrees. Okay, so the tension in A is 430 newtons. Okay, we're being asked to find B. So the force in B is what? Okay, and this question is quite nice because usually we're given the weight or whatever's being held up and then we have to do things with that. But we've already been given the tension in A, so that's nice. So that makes it a heck of a lot easier. So what we can do is just say that the horizontal components of both these forces are equal to each other. So therefore, we can say that 430 cos 35. If you don't know where I'm getting that from, have a look at my easy vectors trick video. We're turning through the angle, so we use cos, and we want a smaller number, so we times by cos, not divide. So that's then going to be equal to this unknown force F cos 12. So all we have to do then, rearrange it, pop cos 12 over the other side, and we end up with 360 newtons. Nice question so far. 3.2, we're given the area of 7 times 10 to the minus 6 meters squared, and the original length is 150 meters. We're being asked to find the extension, so delta L is equal to what when the tension is 430 newtons, and we're given the Young modulus as well, which is 210 gigapascal. So I'm going to say that's 2.1 times 10 to the, well, giga is 9, so there's 10, 11, which we know is a fairly standard magnitude for Young moduli. So let's crack out our equation for Young modulus. E is equal to FL over A delta L. We're looking for delta L, so just swap over these two. So therefore delta L is equal to FL over AE. So just popping everything in. Easy peasy. Lovely paper so far. 430 times that original length, 150. Of course, a long old thingy, isn't it? I guess this is for a football pitch, that kind of thing. So divided by 7 times 10 to the minus 6 times the Young modulus. Could we tidy up some powers of 10? Yes, why not? So we have minus 6 and then 11 on the bottom. So we can just take away 6 from 11. So we end up with times 10 to the 5. And we end up with 0.04. We can go to 2 sig figs. Yeah, 2 sig figs. So 0.044 meters. 3.3, we're going back to our diagram here. We're told that the camera is moved horizontally to the right. The tension in A is now different. Deduce whether the tension in A has increased or decreased. So it's moving to the right, so it's now over here. So we have this, and then we have this. Still have our forces there. And we said this was 360, didn't we? So let's go for what's going to happen eventually. Eventually, we're going to reach the opposite. It's going to be 12 degrees on this side, 35 degrees on this side. So actually, the forces will swap. And so that means that if we move it to the right, force on A will decrease, force in B, tension in B, whatever, will increase. We could add the extra thing of as vertical components must add up to weight of camera. 3.4, okay, optical fibres. So we have X and the diameter is 8 micrometers and then Y is 50 micrometers. Deduce which fibre allows a greater pulse transmission rate. Well, it's of course the thinner one. Thinner is better as it reduces effect of multipath dispersion. The whole idea that, well, you'll end up with one doing that, and then you'll have another ray doing that. And so as it goes around bends, they'll take different paths, and therefore they'll take different times to arrive. I guess they don't like the term multipath anymore. We should call it modal dispersion. Let's go with that. So if we have less modal dispersion, this means shorter pulses can be used because there's not going to be as much overlapping of pulses. We could also say reduces pulse broadening. Question 4, scintillation counters detecting beta particles. Explain how photons are produced by collisions between beta particles and atoms. So beta particle is fast moving electron. It collides with atomic electron and imparts some energy. It's a posh word, gives it some energy. Atomic electron is raised to a higher energy level. So like this, as it de-excites, it emits a photon of energy equal to difference in energy level. And then we always add in there E equals HF as well. There we go. Surprised that's 2 marks. There's 4 points there. 4.2, photon of light enters the PMT. Physics and maths tutor? No, photon multiplier. So the longest wavelength of light that we can make is 630 nanometers, or 6.3 times 10 to the minus 7 meters. Calculate the minimum photon energy required to remove the electron. Right, we know that photon energy is equal to hf, but we have wavelength, so that's of course going to be equal to hc over lambda instead. So we just need to pop the numbers in, not even having to rearrange. Divide that by that. Should we tidy up some powers of 10? Yeah, why not? We might as well. So we end up with minus 7 on the bottom, 8 on top. So we could add the 7 onto the top. So we end up with 15. And we end up with an energy of 3.16 times 10 to the minus 19 joules. But our data has been given to, as per usual, 2 sig figs. At least we're assuming it's 2 sig figs. So we're going to say that's 3.2 times 10 to the minus 19 joules. 4.3, the PMT consists of evacuated glass tube, and we have this. Okay, the electrodes, anode and photocathode, we have the EMF is 3 kilovolts. Okay, calculate in joules the maximum kinetic energy transferred to the electron when it accelerates from the photocathode to the first electrode. Okay, so we have 4 resistors, don't we? And they're sharing that 3 kilovolts. So that means that the PD between the photocathode and the first electrode, that is going to be a quarter of that. So therefore it's going to be, well, 1.5, so 0.75 kilovolts. So it's going to be 750 volts. And if we're accelerating an electron, we know that it's gaining kinetic energy. So therefore we can say EV is equal to half mv squared. Something that people often forget. We don't use it that often, but we know that energy is equal to QV, charge times voltage, so it's EV for an electron. We're just looking for the kinetic energy, so therefore we just want EV. So that's 1.6 times 10 to the minus 19 times 750, and that gives us 1.2 times 10 to the minus 16 joules. 4.4 hits the first electrode, then it bounces off, blah, 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 blah. We have a graph that shows the variation of current in the ammeter with time due to this pulse. So this is current in milliamps, and this is time in nanoseconds. Determine the number of electrons that flow. No, that means that we have to find total charge. And if we want to find total charge, that means that we have to count squares. No, because we know that charge is equal to current times time, and so that means that we have the area under the graph. Oh no. There's a lot of leeway. I'm not going to do it. They say 140 to 180. I'm going to go bang in between, so I'm going to say 160 squares. The important thing is that we know what each square represents. So we can see that 1 square, how high is it? That's 2 milliamps. And then we times that by the time, it's just 1 nanosecond. So that's 2 times 10 to the minus 3 times 1 times 10 to the minus 9. So that gives us then 2 times 10 to the minus 12 coulombs. Cool. Times that by 160. I think I can do that in my head. So that's 320 times 10 to the minus 12 coulombs altogether. So I'm going to say that that is 3.2 times 10 to the minus 10 coulombs. Okay. But we've been asked for a number of electrons. So we know the charge of an electron is 1.6 times 10 to the minus 19 coulombs, but it's coulombs per electron. One of those times when units are your friends. So we have coulombs per electron. So therefore, what we can do is 3.2 times 10 to the minus 10 coulombs divided by 1.6 times 10 to the minus 19 coulombs per electron. Just e to the minus 1 there. Coulombs cancel. We end up with electrons on top, so that makes sense. And so, well, 3.6 divided by 1.2, that's just going to be 2. And then times 10 to the, it's minus 10 on top, minus 19 on the bottom. So we add 19, so it ends up being 2 times 10 to the 9 electrons. All right, multiple choice, my favorite. 5, which one has the prefixes in the right order? Well, let's look at A, B, and C, D first, because they have smallest being pico for A and B. Yes, that's correct, so it can't be C or D. So it has to be pico to begin with. And then it's nano after that. That's the same for A and B, yes. And then what's different? We have, wait, what? Oh, C. So centi. Oh, that's weird. Yeah, we know micros next, don't we? That's 10 to the minus 6. And then it's going to be C after that. We have 10 to the minus 12, 10 to the minus 9, 10 to the minus 6, and then 10 to the minus 2. It's just hundredths. Question 6. Which diagram shows electron capture? Okay, so let's have a look at A first. We have a proton coming in, good. We have an electron coming in, good so far. That makes a neutron, yes. And then we have the electron neutrino. Yeah, and the W plus boson. This is correct, this is right. The charges make sense. +1 going in, -1 going in, therefore 0 coming out altogether. Lepton numbers, +1 for an electron, +1 for the electron neutrino coming out. So that makes sense. B looks very similar, doesn't it? But instead of W plus, it has W minus. So you might be tempted to go for that one instead. But we can see that we have an arrow. We don't really have an arrow on the gauge boson, the exchange particle, to be honest. But whatever, we can think of it as it taking away positive charge in order to leave it as a neutron. So therefore, yes, it does have to be a W plus boson. 7. Okay, we have thallium decaying to lead. Okay, so we have thallium doing 1, 2, 3, 4, and it ends up at lead, 206 and 82. Okay, so we need to get our proton number up to 82 first. So let's do a beta minus, so that ends up with 82 then. We don't know what it is, we don't care. Oh, it is going to be lead, isn't it? Might as well put lead there. And then we need to, well, if we have an alpha, we have to have an alpha, don't we? We can't just have betas, so let's do an alpha. So that removes 2, so that ends up being 80. And then, there we go. If we do another beta and another beta, we end up with 81 and then 82. Okay, so then let's go backwards. So obviously with a beta, it stays at 206. Again, beta 206. But then doing an alpha, let's just call this, well, this is thallium again, isn't it? I don't know what this is. I can't be able to find out. So then 206, but if that was made by an alpha, then that means that that must be 210. And then again, beta doesn't change it. So the answer has to be 210. So the answer is C. 8, what's the number of up quarks and down quarks in a beryllium nucleus? So beryllium nucleus is 4 protons and 5 neutrons. We know that protons are the POOD and neutrons are the NUD. So therefore we have, dealing with the protons, we have 8 ups due to the protons, and we have 4 down quarks, and then we have 5 up quarks and then 10 down quarks. So therefore altogether we must have 13 up quarks and 14 down quarks. So the answer is B. Which decay of a kaon is possible? So we're going to a pi 0 plus that plus that. Well, no, that doesn't make sense, does it? Because if we're making a positron, this has a lepton number of -1. And the anti-electron neutrino has -1 as well. So therefore lepton number doesn't add up there. Maybe some other things as well, I can't be bothered to find out. So let's go for, oh no, this doesn't make sense either, does it? Look at this. We have just 1 lepton coming out of nowhere. Lepton number isn't conserved. It can't be that either. It can't be B. What about C? K plus. This looks pretty good, I have to be honest. Oh no, it doesn't. What am I chatting? We have +1 charge going to +1 plus +1. So therefore, charge is not conserved. So it must be D. So let's just check it out. K plus going to a positive muon and a neutrino, mu1 neutrino. Yes, a positive mu is a lepton number of -1, just like the positron. Kaon isn't a lepton, so it's 0, +1 for the neutrino. So that makes sense. Let's just check the charge. +1, and 0. That makes sense. No baryons, so therefore that makes sense as well. Strangeness, we don't care about that because it is a weak interaction, so that means that strangeness does not have to be conserved. Okay, we have energy levels, 2 very close together there, and then 1 at the top. Which pattern of lines will be observed? Okay, so let's draw all of the possible de-excitations. Boop, boop, boop. And then we have these 2 here. So we should see 6 different wavelengths. So 1, 2, 3, 4, 5, 6 for A, 1, 2, 3, 4, 5, 6 for B. Okay, we know C and D aren't possible because they both have the wrong number, so it's 3 wavelengths for C. So the only difference is then for A and B is that we have 2 wavelengths that are close together, but we have that double for A, and then for B, they're a little bit more spread out. I don't think it's going to be B. No, it's not. Because we can see that these two are going to be very similar, and these two are going to be very similar. So therefore, that's going to be that, and that's going to be those. Therefore, yeah, it's going to be A. 11. Kinetic energy E, de Broglie wavelength lambda. Ah, classic. De Broglie wavelength is equal to h over momentum. And we need to reconcile momentum and energy. It's one thing that people sometimes forget how to do it. So we want to know how kinetic energy is related to momentum and all that jazz. So therefore, we know that EK is equal to half mv squared. So therefore, times in both sides, I'm just going to call it E. ME is equal to half m squared v squared, which is equal to half times momentum squared. Therefore, momentum is going to be equal to the square root of 2 me. So therefore, momentum is proportional to the square root of energy. So if de Broglie wavelength is proportional to 1 over momentum, as we can see from above here, then that means that it's also proportional to 1 over the square root of the energy. So therefore, if this multiplies by 4, this multiplies by 2, so the whole thing goes down by half. So therefore, the answer has to be a half. So it's going to be A. Not a super easy question, that one though. 12, we have waves on water. Oh, easy, okay. So we just have this. This is time, very important. And we have Z, and we have W. This is, of course, amplitude. This is time period. So therefore, the answer has to be D. That's the easiest multiple choice question I've ever seen. I know I've said that for many questions in the past, but seriously, that was easy. 13, 2 points on a wave are out of phase by 0.41 radians. So we can say phase difference equals 0.41 radians. Okay. What is this phase difference? Oh, in degrees. That's easy. All we have to do is turn that into whole cycles. So divide by 2 pi, but then we need to turn it back into degrees. So then times by 360. So basically just 0.41 times 360 divided by 2 pi. And that gives us 23 degrees. The answer is A. 14, light up wavelength lambda, blah, 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 blah. Which row gives another arrangement that produces the same fringe spacing? So we know that W is equal to lambda D over S. So therefore, we need to have a combination of these things that basically doesn't change. So let's look at A. So that's doubling. That's doubling. That's doubling. Can't be that. What about B? Probably looks a bit better, to be honest. 2 times on top, another 2 times on top, 4 times on the bottom. Yes, that is correct. Has to be B. 15. Okay, we have a diffraction grating. The first order, so when n equals 1, the angle is 20 degrees. What is the highest order visible with this grating? So we want to know what n is when theta is 90 degrees. So let's crack out our equation. N lambda equals d sine theta, but d is staying the same and lambda is staying the same. So actually we can just say that n over sine theta, 1 that is, equals n2 divided by sine theta 2. Just proportionality. So we know that n1 is 1. This is 20 degrees. We're looking for n2, and sine theta 2 is just going to be 1 because it's the sine of 90. So actually we just have 1 over sine 20 equals n2 over 1. That just disappears. Therefore, n2 is equal to 1 over sine 20. And that gives us 2.92. So therefore, the answer has to be 2 because we will never see that third order. So that means that the answer is A. Speed of light decreases by 40%. What is the refractive index of the medium? Okay, so speed of light to begin with is 3 times 10 to the 8. And then speed of light afterwards is 40% less. So it's just going to be 60%. So it's going to be 60% of 3 times 10 to the 8. Or in other words, 0.6 times 3 times 10 to the 8. We know that refractive index is equal to speed of light divided by the speed of light in the medium, because we know it has to be greater than 1. So actually we can just say that's equal to speed of light divided by 0.6 times the speed of light. C's cancel. We just end up with 1 divided by 0.6. So what is that? That is 1.67, 1.6 recurring, so it's just 1.7. So that means that the answer is C. 17. Which row describes charge and impulse? Charge is a scalar, yes, so it can't be C or D. Impulse is a vector because it's change in momentum, therefore the answer has to be B. Easy. Next question. 18. Object is in equilibrium. Which diagram is correct? Definitely not C, is it? Because, well, we got them pulling upwards. There's nothing pulling downwards, so it can't be that. D, similar for that one, isn't it? It's going to go off in that direction. What about A and B then? Interesting. Well, if they're drawn to scale, are these drawn to scale? I guess they are. Anyway, whatever. We must be able to top and tail them so they all add up. So let's look at A. This one down here, this force here, that has to balance these two, but I think it's just a little bit too long. So I don't think it's going to be A. I think the answer is going to be B, but apparently it isn't. I don't agree with that. I think that that vector is far too long. Maybe it is actually. Maybe it is. I don't know. So if we take this one and then we add on the one going to the right and then one going up, they should make just a right angle triangle. I guess for B, these ones are far too short in order to balance that one. It's not going to happen. We'd end up going across and then up like that and then down like that. We wouldn't end up where we started. There we go. It's a bit, I still think it's a little bit long. I don't know. I think it might be an optical illusion. You should just draw it yourself. I think they do add up. Whatever. What is represented by the area under a force time graph? Of course, it is impulse, but we're not given that as an answer here. We're given momentum change, and that is the same thing as impulse. So therefore the answer is C. 20. Two horizontal forces. All the forces have the same magnitude. Which system produces a couple about any point inside the object? Definitely not A, because they're not going in opposite directions, are they? We know it's D. We know it's D. They're opposite. They're going in opposite directions. They're equal distance away from the center, whatever. We know that's right. It's the only one with opposite forces. Easy. Okay, moments. Here we go. We have this here. We have a pivot. We have 70 centimeters. And we have 5 newtons pulling downwards there. What is the magnitude of the resultant moment when the student releases? Oh gosh, okay, right. Oh, right, we have the thingy, don't we, down there? I think I should have done this on the opposite bit here. Well, let's rub that out. Okay, so student holds the ruler. What is the magnitude of the resultant moment? Okay, fine. So that's all we have to do. We have to find out the resultant moment. So we have 2 moments, one due to the ruler, one due to the weight. So therefore, ruler. Okay, so let's deal with the ruler first. How far is it away from the pivot? Well, it's 0.5 to there, 0.5 meters. And we do need to be dealing with meters because our unit for the answer is Newton meters. So therefore, this is going to be 0.2 meters. So the ruler moment is 0.2 meters times the 2 newtons. And so that gives us 0.4 Newton meters. And that's going to be anti-clockwise. Doesn't really matter. And then the weight, that's going to be, how far is that away? That's 0.3 meters away from the pivot. So 0.3 meters times 5 newtons. What's that? 1.5 Newton meters. And that's going to be clockwise. It's not in equilibrium. We just want to know the resultant moments. So we just do 1.5, take away 0.4, and that gives us just 1.1 Newton meters. So the answer is C. 22, we have a speed against time graph, and we're being asked what the displacement time graph is. Okay, so let's have a look at A. We can't have distance decreasing if the speed is just always positive, which it is. So it can't be A, and it can't be C either. Let's have a look at B and D then. So let's have a think. We have a 0 speed to begin with, but then we're reaching a max speed here, and then it goes down to 0 again, doesn't it? So therefore, we should have a slowly increasing distance, and then it should increase very quickly because of that fast speed. And then it levels out because at the end, the distance shouldn't be changing. So the answer is B. 23, two ball bearings. Okay, we have X has a mass of 2m, speed u. Oh, I've seen this question before, I know it. And Y, oh, it's vertical as well. And then Y, mass m, 30 degrees to horizontal. So it's doing that 2u, and then that's 30 degrees. Which statement is correct? All right, so A, X and Y have the same momentum. So we know momentum is equal to mass times velocity. That's not true because they're going in different directions. So that's not possible. They might have the same magnitude because it's just going to be 2m times u for X and then m times 2u for Y, but they're going in different directions. So that's why it can't be A. B, X and Y reach their maximum heights at different times. Oh, really? Okay, so let's figure out what this is. Well, this initial vertical velocity is going to be 2u times sine of 30. Now, sine of 30, you might know, is a half. So therefore, that's 2u divided by 2. So that's u. So therefore, they both have the same initial vertical velocity. Therefore, they are both going to go up and come back down in the same time. It's just one's going to go across as well. So therefore, it can't be B either. C, the maximum height. Oh no, it can't be that, can it? Because we've just seen they have the same vertical velocity. So therefore, it has to be D. Let's just check it. X and Y reach the ground at the same time. Yeah, we've just proven that, haven't we? Because they have the same initial vertical velocity. 24, which row is true for an elastic? Okay, fine. Elastic collision, we know that KE will be conserved, so therefore it has to be A or C. Momentum, it's always conserved. The answer has to be A. Found a new easiest multiple choice ever. 25, drag force is equal to kV squared, where K is 64. And the boat's engine has a useful power output of 8,000 watts. What's the maximum speed of the boat? We know that P is equal to FV. Therefore, power is equal to that kV squared times by V. So therefore, P is equal to kV cubed. We want V, so that means V is equal to P divided by K cube rooted. Or to the third, whatever you want to say. Let's do it that way, actually. So that is 8,000 divided by 64 to the power of a third. Let's see what that ends up being. That ends up being 5 meters per second. So the answer is B. 26. Okay, so we have force increasing, right? So let's think about the graph that we have, F against X. Now we know we have this straight line, and it's the area under the graph that gives us the energy. Well, we're looking for an increase in energy. So we're looking for the area of this part here, where this is X1, X2, F1, F2. So it's a trapezium, therefore the difference in energy is going to be the mean height, so F1 plus F2 divided by 2, times by the width of this, so that's X2 minus X1. So the answer is C. 27. What's the force extension graph for a brittle material? It's going to be D, isn't it? Just snaps suddenly right at the top and a very high gradients as well. So a really high Young modulus, but it doesn't have a plastic region like we see with B or A. 28. Oh boy. Which component is an ohmic conductor with the greatest resistance? Okay, is A ohmic? Basically, is the current going up in regular intervals? No, it's not. So it can't be that because it's going 0, 0, 0.1, etc. It can't be that. Is it B? It could be because it's going up in 0.3s. Could it be C? Yes, it could be C as well because it's going up in 0.4s. D, no, that's not going up in equal intervals. It starts off, but then at the end it ends up going up in 0.1, so yeah, it levels out, so therefore it can't be that. So therefore we want the one with the greatest resistance out of B and C. We want the greatest R, so that means the lowest current. Yes, you could use Ohm's law if you want to, but it's fairly obvious that it's going to be B. 29, what shows the resistances of an ideal ammeter? We should have 0 resistance for an ammeter. What about a voltmeter? We should have infinite. So therefore the answer is C, because we don't want current to leak through anything that's in parallel with our component. 30, the capacity of a portable charger. Oh boy. So one charger has a capacity of 1,800 milliamp hours, so that's 1.8 amp hours, a working voltage of 3.7 volts. What's the energy stored in this charger? Okay, so, oh, okay, fine. That's dumb. We can say that energy is equal to power times, so VIT. We already have IT right here, but that's going to be 1.8 times 3,600 because amps is per second, isn't it? So therefore, to find out the energy, we do 3.7 times 1.8 times 3,600. That's a weird way of asking that question. It's really dumb. I do not like that at all. And so we end up with something around 24,000 joules, or in other words, 24 kilojoules. Not a nice way of asking that though. Filament lamp, we have a resistance of 12 ohms and we have a power of 36 watts. This looks identical to the previous one. How much charge flows in 15 minutes? So that's going to be 15 times 60, isn't it? It's going to be 900 seconds. Fine. So we have a question with charge, so we know it's going to be something to do with current. So we can say power is equal to I squared R. So worth finding out the current first? Yeah, let's find out the current first. Therefore, current is going to be equal to the square root of P over R. So it's the square root of 36 divided by 12. So square root of 3. And we know that Q is equal to IT. So we're just going to say, skipping a step, square root of 3 times 900. So we end up with 1,560 coulombs. So it looks like the answer is going to be B. Yeah, it's quite far off though. 1.6 kilocoulombs. Kilocoulombs? Gosh, that's a lot, isn't it? 32. Resistor of... Okay, right. So it's just rearranging our resistivity equation. Rho L over A. But we know that area is pi d squared over 4, because it's pi r squared, but then radius is half, etc., etc. So therefore, resistance is equal to rho L over pi d squared over 4. We can stick the 4 on top there, so that's equal to 4 rho L over pi d squared. And so then we're just looking for diameter, so all we need to do is swap over diameter and resistance. Therefore, d squared is equal to 4 rho L over pi r. So it's the square root of 4 rho L over pi r, but none of those make sense, but C and D have a 2 on the outside, so actually we can just stick 2 out in front. And so the answer is C. Gosh, this looks complicated, doesn't it? So we have 2 branches, so we can pretend that the whole thing is something like, I don't know, yeah, let's do 6 volts because that's easily divisible, isn't it? So therefore, the potential at P is going to be, so, well, let's say that it's 6 volts here, 4 volts here, so it's going to be 2 volts there. And then over here, what? It's 20 and 20, guys. We know it's going to be half, so therefore it's going to be the same there. So the PD between the points is 0 volts, so the answer is A. It's not often you get a trick question like that, to be honest. Finally, 34, we have a potential divider with a thermistor. We're being asked what happens to the PD and current when the temperature goes down. You should know that when the temperature goes down for a thermistor, its resistance goes up, it does the opposite to a filament bulb. So therefore, if its resistance goes up, then therefore so does its share of the voltage. So that goes up, so therefore it has to be A or D, can't be B or C. And of course, if its resistance is going up, then the total resistance is going up as well. Therefore, that means that the current goes down. So therefore, the answer has to be D. Hope you found that helpful. If you did, please leave a like. Consider clicking that super thanks button. And if you want to click on the card, it'll take you to the AS paper playlist. If you need any help, then join the Discord, link in the description. Good luck with your revision. I'll see you next time.